Newman projections, here we go. I tried to make this molecule here pretty much as simple as I can while still getting some key ideas of Newman projections in place. So first of all, whenever you have a Newman projection, it's what you are seeing is first and foremost, you are seeing the front carbon of a carbon-carbon bond. So the bond that we're going to be looking down, when we say looking down, it means looking along the bond. We're going to be looking down along this carbon-carbon bond. Okay, so this is the molecule that we're trying to represent. And again, we're going to be looking along this line. So as you may see in the textbook or elsewhere, you'll see like an eye drawn along a certain bond, and then maybe a diagram like this, and then you will see the Newman projection as a result. So as I'm looking down this bond, what I see is I see two hydrogens. So I'm going to even take away the backside here. I'll fully take away the backside so that we can isolate what we're seeing in the front carbon. So we have hydrogens going down, and then the OH going up. Okay, again, you can look at it from the side. You have these two hydrogens and one OH group. Okay, so that's what you would see on the front carbon. And typically you'd have the big circle out here, and then you have a point in the center from which you're drawing these three groups. So these are always going to have a 120-degree angle to each other when you're looking down the plane. In reality, it's the 109.5 angle, but when you're looking at the projection, they are 120 degrees this way, right? In reality, this angle here is 109.5, but then when you turn it slightly, the projection is 120, just to be super clear. Okay, so now I'm going to put back on, I have, again, keeping it super simple, but still meaningful. I have two hydrogens and then a methyl group. So I'm going to put the hydrogens on and the methyl. Okay, so we're still looking from, maybe could have said this even more explicitly before, but the front carbon that we're analyzing is this one. And then the back carbon is the one with the two hydrogens and the methyl. Okay, so we're still looking from this perspective. Okay, so we have our hydrogen down to the, I don't know how this is going to show up for you, but down into one way, down into the other way, and then the OH going straight up. And so the way I've configured this right now, we have the methyl going down. And if I turn this around briefly, and I'll remove this just so we can isolate the back carbon. You have the two hydrogens going up on either side of each other, and then the methyl CH3 going straight down. Okay, and so what the Newman projection helps articulate is this idea of a dihedral angle around a particular bond. So this bond in question, we're saying what is the angle between these two separate planes of the molecule. Again, we're rotating around a particular bond. What is the dihedral angle around that bond? So the way that we have this particular guy here, we could say that the dihedral angle is, if we want to reference the two main groups that are coming off of this, the OH and the CH3, this orientation that we had before would be a 180 dihedral angle. So again, we're looking down this bond. So what you see from the projection here, you have the OH going up, you have four hydrogens kind of in the middle, and then you have the methyl going down. So the dihedral angle is 180. And what we would say also is that the OH and the CH3 are anti to each other. Okay? So they're anti right now with the carbons completely lined up here. Okay, so you have 6 different groups oriented around the center, and when you have this is also what's called a staggered configuration. So you have two different relationships that you pretty much can have, either staggered or eclipsed. So staggered, generally speaking, is going to be more stable than eclipsed. So here's what it looks like to have eclipsed. This is one of the eclipse conformations. You see that you can't even really see the groups in the back, other than maybe this methyl because has more hydrogens. But the hydrogens that are sort of peeking out from behind, if I line them up in such a way, you don't even see them. Right? So I'm touching a hydrogen right now. There he is peeking out. This is eclipsed. Okay, so we had staggered. Okay, staggered there. So you can see all of the different groups, all 6 groups, 4 hydrogens, 1 OH, 1 CH3. And then eclipsed, like a solar or lunar eclipse. So you can't see them in a true sense. But in order to actually indicate what these groups are, you may see eclipse drawings that are a little bit off kilter, just like something like that. So that you can, or basically what it could represent is that you're tilting, it's eclipsed, but you're tilting it slightly so that you can still indicate what these groups are. Okay, something like that. Just a little tilt. Still drawing the front carbon as a point, and the back carbon, by the way, you draw as the bigger circle. We'll get more to that in a second. So let's go back to this eclipse conformation. Excuse me, staggered conformation. So we have the staggered conformation where you can see all 6 groups. The degree relationship between this oxygen and this hydrogen is 60 degrees. Right? So we have a 120-degree relationship between these two on the same front carbon. Basically, in the middle is this guy for the staggered. So 60-degree relationship here, 60-degree relationship here. And we have, 60-degree relationship between this and this. This and this. And so on around the circle. So again, we have staggered and eclipsed, and you alternate between staggered and eclipsed. Let's see, we said this was our kind of original eclipse form here. So as we rotate every 60 degrees, we go between staggered and eclipsed. So this is our original staggered that we looked at. So if I rotate it again, this is eclipsed again, but now you can see the methyls over here. Okay, I'm going to rotate it 60 degrees again. Now this is a staggered conformation, but now you can see the relationship between these two main kind of bigger groups, the OH and the CH3. Now their relationship is at 60 degrees. So we now could say that the OH is anti to this hydrogen in the back here. So OH going up, and the hydrogen going down. Those are anti to each other. But the OH and the CH3 are gauche to each other. Gauche is another way of saying 60 degrees from each other. Okay, so you see that smaller angle between the OH and the CH3. So the energy, the relative stability of this gauche arrangement is lower compared to the anti-configuration between the OH and the CH3. So if the stability is lower, that means the energy is higher in this arrangement. Okay? So, but nevertheless, it is more stable than the fully eclipsed where you have the CH3 and the OH basically knocking into each other over here. So in general, the eclipsed are going to be less stable anyways. So you have, when you're drawing the energy diagram, you can see this in chapter 2, I think, where you have the eclipsed versus the staggered energy diagram, and you have it going up and down. When you have something like this, you will see a local, well, in this case, you'd have an absolute maximum of the graph in this configuration, where the OH and the CH3 are directly lined up. You would have a local minimum in this. Here, we had the back one rotating. So a local minimum when you have this orientation, 60 degrees, gauche relationship between the OH and the CH3, a local minimum, but still higher energy compared to all the way staggered anti. Okay, so anytime you have an eclipsed conformation, so even though this is not the absolute maximum, this would be a local maximum. And we can go into some of the textbook drawings where we see that as well. So this is, again, eclipsed, but not the absolute maximum. Local maximum, lower than the absolute maximum, but still higher than any of these staggered conformations. And this would be both a local and absolute minimum with the OH and the CH3 anti to each other. And again, in terms of drawing these, you have a point in front representing the front carbon. And so you draw lines all the way out to the groups that front carbon is attached to. So 3 lines, all 120 degrees apart, equally spaced. And that represents the groups, again, that the front carbon is attached to. So the big circle that you see behind that point, the main circle in the Newman projection, actually represents this back carbon. So this is our front carbon or back carbon. And then that from that bigger circle, the groups that it is attached to, let's see, the groups that it is attached to, this guy, the methyl, and this hydrogen, those are also going to be 120 degrees from each other, evenly spaced. And in this particular staggered conformation, you would have the OH pointing straight up and the CH3 pointing straight down. And then you'd have the spokes coming off of the back carbon going up for the hydrogens. And so generally what you'll see is the lines for the front one are a little bit longer, and the lines for the back one are a little bit shorter, such that all 6 groups are basically in the same, and we'll see this on an actual drawing, but they are basically the same distance from the overall center of the circle. So they're at the same radius from each other. That's pretty much all I got from this guy, and we'll look at this now in the textbook, some drawings of it. So here we are now in chapter 2, and here is what the Newman projection energy diagram looks like when you have just ethane. So you have H's on both carbons. And you can see the local and absolute minima are the same. There's no differentiation there. So whichever eclipse conformation you have is both a local and absolute maximum, and any staggered conformation you have is a local and absolute minimum. And you can see 12 kilojoules or 2.9 kilocalories is the difference between the max and min. Okay, and yeah, you can see the Newman projections there, and what we talked about, which is that the center, the point in the middle of the circle represents the front carbon, and you can see the longer lines coming off of it. And then you have the circle, which represents the back carbon, having the shorter lines coming off of it, and then all 6 of the groups are sort of evenly spaced, and you can see that even more in the eclipsed conformation, where they're literally right next to each other, as opposed to like one being higher and one being lower. So more in line with what we were just looking at. Obviously, in one case we had OH instead of two different CH3 groups, just so that you could see a little differentiation. But we're going to see the same principles working here. So we have this idea of the anti-conformation versus gauche conformation of 60 degrees. You can see this is 300 degrees, but it's an absolute value of 60 degrees between the groups themselves. And then again, the energy diagram that corresponds with it. So we were saying that we have an absolute maximum when we have eclipse conformation of the two main groups eclipsed on top of each other. And again, gauche is going to be higher energy compared to the anti, but it's still a local minimum on this energy diagram. So whether you have the two CH3 groups in this case being eclipsed, or you have a CH3 and an H eclipsed, both of those are going to at least be local maxima. But the two CH3s eclipsed is the absolute maximum. And again, gauche, you have a local minimum, but it's when the CH3 groups, or in our case, the CH3 and the OH groups, when they are anti to each other. And once again, we see the, let's look at the anti relative to our diagram here, or our ball and stick model, shall we say. Yeah, so this is why I had it just on myself earlier with no screen sharing. Let's see, can we get this right? Something like that. Okay. So yeah, you see the H's coming up and going down slightly, and then you have the axial, so to speak, OH in our case, and then the going down CH3. However, in this case, that if just to keep us in line with the way that they've drawn this here, the front carbon they have with the main group going down, just so that you have a different view of that. I hope this is not too confusing. So the main group going down, and then on the back carbon you have the main group going up in this particular diagram. So that's pretty much the long and short of it. I hope this helps, and we'll go from here. But yeah, we have our anti and our gauche, our eclipsed and our staggered. In general, the staggered are more stable and the eclipsed are less stable. And if we're comparing anti versus gauche, anti is even more stable. Okay, and then this be maybe the last important point is that it's a 3.7 kilojoules or 0.9 kilocalories per mole difference between the most stable anti-configuration and the gauche configuration. And this is responsible when we have, this is specifically when we have the CH3 groups interacting. And so this is what we call our gauche butane interactions, because this is of course gauche butane, or again, what we call 1,3 diaxial interactions here. So in this case, obviously makes more sense to call them gauche butane interactions because that's what they are. And specifically when we're saying 1,3 diaxial, we are referring to the one carbons hydrogens with the 3 carbons methyl, or vice versa. The 1 carbons methyl with the 3 carbons hydrogens. So those are technically what are actually axial to each other. But that's sort of a secondary or even a tertiary point. We're focused on the actual Newman projection construction themselves, Newman projection construction itself, and the relationship between these groups. How the point represents the front carbon, And then the big circle in the back represents the back carbon, and the lines coming off of the back carbon typically are shorter and represent, again, the groups coming off of it. And the groups coming off the front carbon are drawn from the center of the circle. And this is what I was referring to about the eye. Sometimes you'll see that drawn as far as, okay, we are looking from this perspective down this carbon-carbon bond. And then that's what results in the Newman projection. So you can see these, this was going to be a staggered conformation because you have the two groups that are in the plane of the page, one's going up and one's going down. So those are the CH3 groups there. And you see the line and wedge of, you have this hydrogen is on a dash going back, so that represents this one. This hydrogen is on a wedge coming front, and that's this one. So it's towards us from this perspective, but as we're looking from the left, maybe, yeah, I mean, I'm actually pointing from the left, but I think this is flipping my image. So it's from the left, it's from the left side of this page, let's put it that way. This is to the right, so that's why it's this one, and then this one that's going back is to the left. And same deal for this one that's going back is to the left, and this one that's coming towards us from this perspective is going to the right over here. That's all I got. So I hope that helps, and let me know if you have more questions. Cheers.